Welcome to homework.
Okay, when we think about the cyclopropenyl MO diagram, right, we've basically got a triangle, okay? And what we need to do is come up with maybe however many, well, three exactly, right? We're bringing three atoms together, three symmetric ways that these orbitals, p orbitals, could behave, right? So one example would be all the p orbitals in phase, right? And that's got a symmetry to it. Next, we could have one out of phase and two in phase. Okay. And then maybe the less obvious one, but equally important, is if we have one out of phase, one in phase, and then one just not participating at all, right? So in terms of energy, this is going to be the lowest, everything in phase. That's our bonding. This would be our anti-bonding. And this would be non-bonding. Right? So in terms of energy level, what we're looking at is anti-bonding, non-bonding, and bonding. Well, now, when we consider the cyclopropenyl cation, how many electrons do we have in our pi system? Right? Each of these, okay, we're going to have obviously 2 electrons in this double bond, but there's no electrons here, right? There's no electrons in this empty p orbital, that is, right? So we only have 2 electrons. So if we're going to fill them in terms of energy, right, we're going to get 1, 2, both in the bonding orbital, which means overall it's going to be bonding. And that corresponds to the fact that we've got this planar system, right? Everything's got a pi orbital in that plane. It's cyclic. And we have 2n plus 2 electrons, right? We obey Huckel's rule. 4n plus 2, where n equals 0. So 2 electrons is an aromatic number of electrons, right? And that's agreed with when we consider the molecular orbital diagram as well, right? We're with 2 electrons in this bonding orbital and nothing in the non-bonding or anti-bonding, we're significantly lower in energy than this system would be were it not together in this particular shape.